l'entrée maritime le long sur le pourtour en fait du golfe du Lion. C'est là qu'il fera le plus beau stade aujourd'hui avec pas mal de vent d'autant. Regardez tout cet après-midi, ces entrées maritimes vont se maintenir alors qu'ailleurs la grisaille va se dissiper. Vous allez profiter de cette journée.
Hello, good afternoon, Bodo, and good afternoon, Dr. Muka, and also for the speaker today, Mr. Muhammad Adib Aska, and also Mr. Nanda. So we will start the RFG meeting today on the 6 UTC.
Okay. So, sorry, Kafid, the 06 UTC, is that in 1 hour's time or is it 05? I guess 06 UTC is now,
yeah.
right?
Yes.
And it goes to 08, is that right?
Yeah, until 8 UTC.
All right, thank you. Good to see you.
Yeah. Okay, we start now. Assalamualaikum warahmatullahi wabarakatuh. Good morning, good afternoon, and also good evening, everyone. Welcome to Regional Focus Group Meeting, Indonesia Philip Center of Excellence, February 2026. The Honorable all speakers, Dr. Muka Yameji, Mr. Nanda Alfadi, and Mr. Muhammad Adib Askar, also all participants of this meeting. I'm Hafid. I'll be the moderator of meeting today. I'm very pleased to see you here and welcome all of you to this meeting. Before we begin, I would like to introduce you the presenters today. Our presenters for today are from JAXA, Japan, and Directorate of Public Weather Services, BMKG. And today they will present about the GSMaP product data and its role on the operational meteorology. Before the presentations begin, let me inform you all. If you want to ask questions, please typing in the chat box during the presentation or raise your hand after the presentations from our presenter. So we start to the first presentation by Ms. Dr. Muka Yameji from JAXA. Dr. Yameji working as an expert on satellite meteorology in the JAXA, and she will present about overview of the GP mission and the multi-satellite rainfall product, GSMaP. Dr. Muka, are you here?
Yes, can you hear me?
Okay. Yes,
Thank you very much.
Okay,
Thank you very much.
Dr. Muka, the time is yours.
Thank you very much, and thank you for inviting me to this very excellent opportunity. So I will share my screen first. I hope you see my screen now. Yes, thank you very much, Bodo-san. Thank you very much. So my name is Moeka Yamaji from Earth Observation Research Center in JAXA, Japan Aerospace Exploration Agency. So today I'd like to talk about overview of the GSMaP mission itself and the multi-satellite rainfall product called GSMaP. So here shows the contents of today's my talk. So firstly, I'd like to talk about the GPM mission, Global Precipitation Measurement Mission, including the GPM Core Observatory and a little bit the detail about the features of the satellite sensors. And then I'd like to talk about the GSMaP, Japanese Multi-Satellite Rainfall Product, and its concept of the GPM mission and overview of the GSMaP, use cases, algorithm, validation results in Japan, and data access. So firstly, here shows the GPM core observatory here. So GPM core observatory providing detailed observation of precipitation in combining of a passive radiometer developed by NASA called GMI, GPM microwave imager, and a passive radiometer called a radar instrument developed by JAXA and NICT in Japan. The spacecraft itself was developed by NASA, and also the passive sensor, GMI, was developed by NASA. And JAXA and NICT developed the dual frequency precipitation radar called DPR, which is a key instrument to generate GSMaP. And then the satellite was launched in February 2014 from Tanegashima Space Center in Japan. So before talking about the GSMaP, I'd like to introduce the actual observation data set from the GPM core observatory. So this is a case of Super Typhoon Maria in 2018, and the spatial extent was observed by the GMI, and then the DPR onboard GPM core observatory can observe the three-dimensional structure of the precipitation like this typhoon. So we can know and understand not only the spatial extent, but the three-dimensional structure of the precipitation system. And this information is very important to generate such kind of multi-satellite product called GSMaP or US product IMARCH. And this slide shows a basic introduction of the remote sensing by Earth observation satellite. And left panel shows the wavelengths from the ultraviolet, visible light, infrared, and microwave. So the electromagnetic waves in the visible, infrared, and microwave wavelengths are widely used in the Earth observation from space. And as for the precipitation observation, we mainly use a microwave like this to observe the spatial distribution and the three-dimensional structure of the rainfall information. While the cloud information, like the geostationary Himawari, the sensor mainly use the visible light or infrared wavelengths. And the Earth Observation Research Center, where I belong to in JAXA, develops algorithms to generate products or information from signals directly detected by the satellite observations. And this slide shows the passive sensor or active sensors differences. The space-based observation sensors can be divided to two categories. One is passive sensors, and the other is active sensors. So passive sensors cannot emit electromagnetic waves by themselves, but the sensor receives the electromagnetic waves from the Earth to observe the Earth observation or the Earth environments. So the passive sensor do not emit, but just catch the reflection or scattered signals reflected from the sun, or just catch the signals emitted from the clouds or some other things like this. On the other hand, active sensor emit the pulse by themselves and catch the signals backscattered from the signals, like a cloud or precipitation particles or something like this. So this is a big difference. Emit the pulse by themselves or just receive the signals emitted from the Earth. And in terms of the precipitation observation from space, we have precipitation radar, which can be categorized as an active sensor. So the precipitation radar is similar principles of the observation, like weather, ground-based weather radars. But the difference is the sensor is not the ground-based, but the space-borne precipitation radar. So the sensor can directly observe the vertical structure of precipitations to actively emit the pulse and measure the echoes reflected back from raindrops or snowdrops. So the sensor can detect the vertical distribution of precipitation, but relatively the source is limited to narrow source. And there is currently maybe a few precipitation radars in operation from space over the world. And we have Japan has a long heritage and big heritage from the 1997. And not only the active sensors, there are several types of space-based sensors which can be categorized as a passive sensors. The one is infrared imager, and the other one is microwave radiometer. So GMI can be categorized as a microwave radiometer, and Himawari imager can be categorized as an infrared imager. So as you may know, the infrared imager can measure cloud top temperature. So which is very closely related to the precipitation rate over the ground, but cannot observe directly the precipitation itself. So we need to assume some relationship between the cloud top and rainfall rate. Then we can estimate the ground-based precipitation, but cannot observe directly the precipitation. And microwave radiometer imager or sounder can measure intensity of microwave radiation that is constantly emitted from the raindrops. So the sensor can estimate the spatial distribution of precipitation with wider source. And there are many microwave radiometer in operation globally. So we can use this microwave radiometer for the GSMaP generation. And here shows the GPM DPR observation case of Typhoon Rai, which caused damage in Philippines. So the precipitation information observed by JAXA satellite was also used as one of the information sources in the report, like this kind of event basis report, which was issued by Manila Observatory in the Philippines. And they use our JAXA rainfall information in the report. And in this case, we can detect the eye wall of the Typhoon Rai, and we can obtain the very highly developed precipitation systems up to maybe 20 kilometers or something like this. So this kind of information can help to understand the precipitation events like heavy precipitation, typhoon cases or tropical cyclone cases or something like this. So next, let's move into the GSMaP part, the multi-satellite rainfall product developed by JAXA. So here shows the overview and concept of the GSMaP. GSMaP product. So under the GPM mission, we have the GPM core observatory that I mentioned in the earlier part. And we have some GPM constellation satellites other than the GPM core satellites. So we combine these multiple satellite and generate the one global space-based global rainfall map called GSMaP. GSMaP is our global rainfall data, and spatial resolution is about 0.1 degree latitude and longitude. And we provide various versions such as real-time version for monitoring or long-term gauge-adjusted version for climatological or agricultural purposes. So for now, as of the end of January 2026, we are more than 17,000 registered users from the 163 countries or regions, and plus website users who do not registered here. And the unique advantage of the GSMaP is that the space-based rainfall observations allow us to capture the rainfall even in the area lack of ground-based observations. And rainfall can be measured globally, continuous and same interval and consistent accuracy from space. And GSMaP can be available open and freely through the web-based GUI FTP site and the data cloud platforms like Google Earth Engine. And we provide long-term archive data set for more than 25 years since 1998. And there are many Asian and Oceanian users. And for downloading data, quick registration is required for users. So many Asian users analyze the GSMaP dataset for various purposes. And surprisingly, recently, the registered users from Indonesia was increasing rapidly. So now more than the Japanese registered users now. And we have many Asian users from Philippines, India, Thailand, Vietnam, or something. And as for the Oceania users, they mainly use for monitoring in real time. So website is useful tool for them, and users can use the website without registration, so that many users from Pacific Islands use this website for real-time rainfall monitoring. And not only the weather-related purposes, we confirm many use cases like climate monitoring, water-related disasters, agriculture, energy, public health, education, and so on. So if you're interested in the use cases, not only the weather-related purposes, please visit our corrected book, case studies demonstrated by TRIM, GPM, and GSMaP. You can access from this URL. And next, I'd like to show you some use cases related to some weather or WMO forecast fields. The first one is cyclone monitoring. So space-based information like GSMaP can help capturing the amount and distribution of rainfall even over the oceans and the area lack of ground-based observation. And this information can be used as a complementary tool of ground-based radars in case of any troubles or unavailability. Like this, this is a case of Philippines, and typhoons are usually approaching from the eastern ocean, from eastern Pacific Ocean to the Philippines. But in this case of the super typhoon Lori Goni, which brought many severe damages in Philippines. And at that time, Birak radar here, which is usually play an important role for rainfall monitoring, approaching from the ocean, but at that time, which was destroyed by the typhoon itself. So this kind of emergency case, satellite observation can also useful as a complementary tool. And as for the utilization in Pacific Islands, which I already mentioned, many Pacific meteorological offices use our website to monitor the rainfall approach surrounding area over the ocean. And our GSMaP can be used in real time. So they use our data set as a complementary to monitor especially for the severe rainfall information, like tropical cyclones or something. And from Japan, not only JAXA, but GMA provides the Himawari cloud information. And Himawari has a very high resolution and cloud information. And GSMaP can provide hourly-based, little bit coarse resolution, but directly observed precipitation information. So cloud information by Himawari provides essential information to monitor the locations of the precipitation systems moving by minutes. And in addition to the fine resolution cloud information by Himawari, GSMaP can provide the rainfall information, which is important for the comparably quantitative rainfall monitoring. So this case for typhoon, we cannot identify which area has a heavy rainfall over the typhoon, but when we see the precipitation information by GSMaP, we can identify which area has a very heavy rainfall from the eye location. And tropical cyclones do not always have a symmetric precipitation structure. So this kind of GSMaP information can help to understand the precipitation, the amount, not only the distribution, but amount of the rainfall. And we also preparing the GSMaP island version website for the Pacific Oceania region countries like listed here: Mauritius, Chuuk, Cook, Fiji, French Polynesia, Guam, and so on and so on. And so we prepare some website to support small islands to monitor the rainfall information. And we adjust the local time to suit UTC and also the local time for each island time zone. And default zoom level and center location can be customized for each islands. And not only the weather monitoring, but the GSMaP information can be used for the flood analysis and forecasting. So this case is the collaboration with International Center for Water Hazard and Risk Management under the auspices of UNESCO. We call them ICHAN. And they have developed the RR model that can estimate the large-scale floods worldwide in close real time by using GSMaP. And we also developed the global terrestrial hydrological simulation system called Today's Earth. So to mitigate the water-related disasters, it's very important not only to observe rainfall itself, but also to determine where and how much actual rainfall collects on the ground, like a river. So JAXA has developed a global terrestrial hydrological simulation system called Today's Earth under the joint research with the University of Tokyo. So by using this Today's Earth system, not only the rainfall information by GSMaP, but by inputting the GSMaP dataset, we can use products or dataset like about the not only rainfall, but for many water-related variables. And this is a use case by the BMKG. So they kindly use our GSMaP dataset for their own website available here. And very interestingly and effectively, they monitor not only GSMaP daily or hourly rainfall distribution itself, but they calculate consecutive dry days, which is very important way to use to monitor the dry days in monitoring, which should be effective for monitoring of the dryness of each regions. And also we started to operate a website called JAXA Climate Rainfall Watch, which provides information about the extreme drought and heavy rainfall over the world based on the GSMaP past statistics. So we provide the daily, penta, weekly, 10 days, and monthly data set with a climate normal. So we provide the data set itself and also the graphical user interface website like this. So by using this information, users can use our data set not only to monitor the rainfall, but also the drought monitoring or heavy rainfall monitoring. And different from these purposes, this slide shows the weather index insurance for farmers developed by a Japanese private company. So they use they offer the weather index insurance for farmers of longan in Thailand. Longan and sugarcane in Thailand. So the drought makes it difficult to continue operations when crops are damaged by drought like this. So insurance payments are made when it is determined to be a drought. So that even if crops are damaged, the farmers can continue the agricultural business. This is a model of the weather index insurance. But for this insurance, they need to determine the drought or not drought. So GSMaP is used to determine drought, which is important information for the insurance in the region, lack of ground-based rainfall information. And next, I'd like to quickly explain the algorithm validation results and data access of GSMaP. So as I mentioned earlier, GSMaP is generated by not only one satellite, but also the multiple satellites. Oh, I skipped this. And then firstly, rainfall data from each microwave radiometer is estimated like this. So we firstly get the signals from microwave imager or sounder. Then we use a lookup table, and then rainfall data from each microwave radiometer can be detected like this. And here shows a case of the microwave imager, and we have the microwave sounders like this. So depending on the type of microwave radiometer, precipitation intensity and resolution slightly differ depending on the sensor types. And after that, after collecting these microwave imager or sounder information, we need to use IR infrared imager information by geostationary satellite, like a Himawari satellite. Then here shows a flowchart of the microwave radiometer and infrared merged algorithm. So by using the geostationary infrared imager, which has a high temporal resolution, we can get the geostationary infrared information at present and similar information at 1 hour before the present. By using these two differences, we can calculate the cloud motion vector. Then we apply this cloud motion vector information to apply to the GSMaP at 1 year before present. Then applying this information 1 hour before GSMaP is propagated by the cloud motion vectors. Then during this time, 1 hour, we collect the microwave radiometer data at present, and we overlay this directly observed information to the GSMaP propagated by using the cloud motion vector and merge between this information, and we generate the GSMaP present data set. And also, not only the space satellite-based precipitation estimation, we also use ground-based gauge calibrated rainfall information. So here shows a GSMAP family providing based on multiple satellite, 3-day latency, 4-hour latency, and quasi real time. And these products has its gauge adjusted version. So we have 6 types of the GSMAP like this. And the 3-day latency has more higher accuracy, but if a user use a real-time version, better latency, but relatively lower accuracy. So users can choose which the appropriate GSMAP product for each purposes. So maybe I will skip this part. And lastly, I'll show you some data access information. So as I mentioned earlier, we provide a website to monitor the precipitation like this. And we offer the guidelines how to use a GSMAP dataset like this. And for users who like to download and analyze the data, we provide the information after the registration. So once you complete the registration, really quick registration, then you can get the email from our server, which provide the information, FTP server information. So as a summary, GPM Core Observatory providing detailed observation of precipitation in combination of a passive radiometer and the active precipitation radar. And GSMAP is a GPM's Japanese multi-satellite product by combining passive microwave radiometers, IR imagers, and precipitation radars. So GSMAP consists of some products like real-time, near real-time, standard product, and their gauge-adjusted versions. So users can select the appropriate product according to their purposes. So we distribute the data or image via website or FTP site or other platforms. So that's all from me. Thank you very much.
Thank you, Dr. Murka, for a great presentation about the comprehensive explain the GSMAP product data. Okay, now we move to the second speakers, Mr. Nanda Alfodi from Directorate of Public Weather Services. Mr. Nanda will bring the presentations, multi-dimensional verification of GSMAP precipitation products. Mr. Nanda, please, time is yours.
Thank you, Hafiz. Let me share my screen. Can you see my screen?
Okay, perfect.
Yeah, thank you. Yeah, first of all, let me introduce myself. I'm a weather forecaster in BMKG, and I'm one of GSMAP product users in my daily routine in my public weather services job description. And in this occasion, I will talk about GSMAP precipitation product assessment regarding multidimensional approach. So why I put this term multidimensional? Because I want to assess GSMAP in temporal aspect and also in spatial aspect. Okay, this is my outlines starting from background. Why this is important for me to assess how well GSMAP capture or detect precipitation in Indonesia, and the next one is about data and methods, and then results, and then the last one discussion and conclusion. Why is this important? As weather forecaster, we use GSMAP regarding in weather forecasting operational. We use for monitoring. We monitor where is the location which has heavy rainfall or let's say quite long consecutive dry days to detect or to assess the vulnerability to disaster in Indonesia. And based on the monitoring, we use the result as one of variable in our IBF model. So GSMAP is one of input data for our IBF model or impact-based forecast model in Indonesia. And we also use IBF for bias correction for NWP product. So based on bias or error or differences between GSMAP and NWP, we do some bias correction approach in our operational. And the last one, we also use GSMAP for our NWP verification. So we assess our NWP model based on GSMAP. That is one of our model verification data. And however, as well as the other observation data, of course, this data, which is GSMAP, have a bias both spatially and might be temporally. So this study, or actually this is still a preliminary study or early study for GSMAP assessment that has aimed to evaluate GSMAP skills relative to weather station observation data in Indonesia. And we try to identify meteorological factor leading the bias. So we not only assess the GSMAP skills, but also we try to identify why it happens, why the bias tend to be high in particular area or in particular period. For the method, we divided into four aspects. We try to evaluate GSMAP based on four aspects. The first one is seasonal aspect, and the second one diurnal aspect, and the next one coastal relative distance. So we try to assess GSMAP skill in several coastal relative distance areas. And the last one, we try to assess GSMAP based on intensity. So we want to know how well GSMAP in several intensity categories of rainfall. And for verification indices, for continuous values, we use RMSE or root mean square error, mean absolute error, and then Spearman rank correlation. Why we use Spearman rank correlation instead of Pearson correlation? Because as we know that rainfall or rainfall data will always be extremely skewed data. So I decided to use Spearman rank correlation, and then we also use instantaneous bias, and then scatter plot and box plot. For categorical data, for binary, we use POD, FAR, and then accuracy, precision, recall, and F1 score. For multi-class, we try to assess accuracy. And for time frame or time frame of our study is between January 1st, 2022 until December 31st, 2025. So it is 4 years data. Yeah, this is data processing starting from raw data sources that we use in this study. We use weather station data from 172 stations for 3-hour accumulated rainfall, and GSMaP the last version, version 8, and the product is near real-time gauge calibrated hourly precipitation. This data was processed uh, for several steps or stages. The first one is data extraction, because GSMaP is a grid-based data, so we need to extract the data into tabular data based on weather station data coordinate. And then we try to aggregate into 3 hourly accumulative rainfall, and then we merge the data, and we also did data cleaning for dropping missing data, and then invalid data and outlier. So in this study, we only assess data within 0 percentile until 99 percentile. So we ignore the outliers data, both in weather station data and GSMaP data. And for categorization data, for binary, of course, we divided into 2 categories. No rain for values below 0.1 millimeters, and rain be above 0.1 millimeters. And for multi categories, we use this 8 categories, as you can see in this screen. No rain and up to beyond 50 millimeters. And the final data is this one, more than 1 billion data for our event for this study. And this is the histogram for the data. We can see that more than 75% of data is no rain event, and it is clear that this is extremely right skewed. So this is the reason why I use Spearman rank correlation instead of Pearson correlation. And observation data have a higher extreme value than GSMaP. My preliminary hypothesis is GSMaP tend to underestimate for high intensity rainfall, but we will talk about it further later on. Yeah, for a seasonal scale, we can see that in general in Indonesia, the dry season occur in June, July, August, and September, and it can be captured very well by GSMaP, and but we can see that there is a systematically underestimation rainfall year around in this graph in left top corner or left top graph, and I think it is like a typical characteristic of remote sensing data, because in radar I found the same characteristic that rainfall estimation of remote sensing tend to be underestimate based on the surface-based observation. And for temporal scale, the right top corner graph, we can see that there is a stable correlation, even not very high correlation coefficient below 0.6, but it's quite good, I think, because it is quite consistent or stable, and it is good at tracking timing and variability, because it is correlation coefficient for temporal. So the GSMaP can capture very well the timing of rainfall, but quite weak at reproducing amplitude. And the lowest correlation we can see occur in dry season. And for error behavior, the RMSE and MAE across the seasons, we can see the largest error occur in wet season, and the smallest one in dry season in June, July, August. It is again typical of satellite limitation with deep convection and extreme rain limitation, or GSMaP quite struggle to reproduce the precipitation when it is produced from deep convection, or deep convection, or cumulonimbus cloud. And then detection skill, it is quite promising if we see the accuracy value, because across the seasons from December until November, we can see the accuracy is above 0.7. So it is reliable for detecting did it rain, but less precise again for how much. And for diurnal pattern, in general, diurnal timing for peak of rainfall observed in 9 UTC, and GSMaP observed in 12 UTC. So there is a 3-hour phase lag. And based on this graph, better performance in night hours. Oh yeah, this is why I divided into several regions, because in Indonesia, because we have quite wide area, the local pattern or diurnal pattern will be different for each regions, because uh, uh, different coastline, different what is it, longitude position. So I decided to divide the Indonesia region into these several areas. Yeah, and we can see that for amplitude, GSMaP signal like smoothed, or what is it, underestimate best compared to weather station data, or underrepresenting peak convection during afternoon time. So it is again, I think it is typical characteristic of remote sensing data. And for error structure, I think for bias, it is quite good because GSMaP produce a very small bias, and the largest spread and errors occur during convective peak or during afternoon. And for detection skills, the right graphs, we can see that in general, based on average CSI, uh, it is a moderate skill and better performance in night hours. It is the same with the previous one. So during night hours, GSMaP shows the better performance. And for coastal relative distance, we can see that clear coastal gradient in performance based on the left graph. Skill improve from coast to coastal area to inland. And for detection skill for coastal or less than 20 kilometers from coastline is the lowest skill, and the highest skill occur in inland, or the area with the distance from coastline beyond 100 kilometers. And for correlation, we can see that increases inland. So the best correlation observed in inland area, and the lowest RMSE or root mean square error observed in coastal area. So it is a bit tricky to decide the best performance, because if we talk about the bias, the lowest bias or lowest error captured in coastal, but for the temporal aspect, inland area will have the better performance compared to coastal area. Okay, for elevation, we try to assess GSMaP performance based on elevation of each stations, and we can see that it is clear that there is a elevation effect in GSMaP performance, which performance decrease with increasing elevation. It is clear in left graph based on accuracy, binary accuracy, and multi-category or multi-class accuracy. And for correlation, it is quite same, but yeah, for correlation, in general, the weakest or yeah, the lowest correlation captured in low elevation, the lowest elevation below 200 meters, and the highest one captured in the highest elevation between 1,000 until up to 2,000 meters. And based on intensity of rainfall, the interesting thing is based on this box plot, we can see that the bias increase along the intensity of rainfall. And it is interesting because if we try to use GSMaP for assessing the vulnerability of hazard or disaster, we need to aware about this one, because it is important to assess the underestimation or overestimation of our observation data, which is GSMaP. And for detection skill of GSMaP, we can see that POD in this graph, POD drops sharply with a higher threshold, while false alarm ratio increases. And for this intensity 50 or beyond 50, FAR or false alarm ratio becomes 0, because I think there is no GSMaP value beyond this threshold. So that's why false alarm ratio becomes 0. But basically, based on this graph, we can see that there is intensity driven performance if we assess the GSMaP based on this threshold. Okay, for more explained these findings for the large scale, I mean for seasonal aspect, GSMaP successfully reproduced the seasonal phase of monsoon, indicating the sensitivity to large scale atmospheric circulation and moisture transport. GSMaP shows the impressive performance regarding the seasonal pattern because it is more large scale pattern or large scale moisture transport. And for intensity driven skill, based on the finding, we can see that skill decreases significantly with increasing rainfall intensity. And like Moika mentioned that in GSMaP, it also use a passive microwave. So this this is the I think this is the sources of error or bias. It is also confirmed by previous study, which said that passive microwave retrieval rely on ice scattering signal. So which do not scale linearly with surface rainfall, causing systematic underestimation heavy rainfall. And independent innovation, which is from previous study, confirmed that correlation decreases and error increases as rainfall intensity rises. And topographic influence on accuracy or skill of GSMaP. It is also plays a role in increase or decrease of GSMaP skill, which model skill decline with increasing station elevation, highlighting the impact of terrain complexity. And there are several studies confirm about it. So if we use GSMaP in complex terrain or complex topography, we need to aware about this limitation. And for coastal effect or coastal relative distance area, it also there is a strong correlation regarding this aspect. So rain detection performance decrease in coastal area where satellite pixels include mixed land and ocean signals. And this surface emissivity contrast between sea and land complicates microwave retrieval and reduce rain and no rain discrimination. So it is important to know. And apparent contradiction. Maybe some people here think that the highest performance based on topographical feature uh, captured in high land or high elevation. But for the coastal term, the highest performance captured in coastal area, and it looks like contradictive, but actually it is not contradictive. It is like uh, different source of error because in coastal aspect, coastal error mainly arise from surface emissivity heterogeneity, and for mountain errors or topographical error arise from precipitation, microphysics, and spatial variability. And there are some studies, some previous study talk about this context. And for regional characteristic of the maritime continent hosts some of most intense convective system globally, of course, because a lot of convergence here, a lot of surface surface heating here in Indonesia, and it is strengthened by archipelagic country. So there are a lot of moisture here, and it creates significant challenges for satellite rainfall retrievals. And despite these challenges, GSMAP can still reproduce key rainfall patterns such as diurnal cycle and general precipitation distribution. And implication for operational, especially for me as weather forecaster, GSMAP is suitable for rain occurrence detection and climatological and seasonal analysis, but we need to aware about the limitation. The first one, extreme rainfall estimation. The second one, complex terrain issues, and then coastal transition zones. So uh, I think for the last one, we need to do bias correction and gauge integrations that substantially improve performance and should be applied for hydrological and hazard application. And I think this is the future work for the next project for this what is it, serial study research serials. I think that's all from me. This is the reference list, and thank you.
Okay, thank you, Mr. Hernandez, for the insightful presentations on evaluating GSMAP product data over various topographies, especially in Indonesia regions. For the last speaker, Mr. Muhammad Adib Aske from Directorate of Public Weather Services. He working as expert on the satellite meteorology divisions. So he will bring presents about the utilization of GSMAP satellite data for consecutive dry days monitoring in Indonesia. Please, Mr. Aske, time is yours.
Thank you for inviting me. I will share my screen. Okay, can you see my screen?
Yes. Could you please do full screen, Mr. Aske?
I cannot full screen in this. I think it's can be see in the Zoom.
Yes, we can see, but it's
Okay.
not full screen.
Aska, you
Okay.
can use F11 if you want to full screen mode.
Okay.
Okay,
Yes,
nice.
perfect.
Okay. Thank you for inviting me. Thank you for the time. Let me introduce myself. My name is Muhammad Atibaska. In this presentation, I would like to explain about utilization of GSMAP satellite data for consecutive dry days monitoring in Indonesia. Okay, this is the outline of this presentation. Firstly, I will describe natural disaster in Indonesia and why satellite-based rainfall is important, and then we will discuss about overview of GSMAP satellite precipitation and also GSMAP products, including its characteristic, and also we will move to consecutive dry days and how we calculate it, and the next is data processing workflow. And we will discuss about case study and limitation, and the last is conclusion. Okay, firstly, we talk about natural disaster in Indonesia. All we know that in Indonesia have natural disaster almost all year. In December until January and February, we are in peak rainy season. There are many disaster potential such as floods, landslide, and high waves. And next month, March until May, which is the transition season, we also have natural disaster potential such as tornadoes, lightning, and hail. And in June, July, and August, we also have natural disaster potential such as drought, forest, and land fires. And September until November, we also have natural disaster potential forest and land fires. During the month July, August, September, and October, forest and land fires commonly occur in Indonesia, with Sumatra and Kalimantan being the most affected regions. And this is natural disaster in Indonesia, a disaster occurrence based on BNPB data from 2019 until 2025 data. We all know that Indonesia is generally known as a humid region, but in certain conditions, there are strong El Nino and Austral monsoon make significant impacts. The impacts is increased drought, forest and land fires, and consecutive dry days are signal of this disaster. We can see that in the El Nino years in 2023, the forest and land fires reaches 2051 in the incidents or event. And also in the last 3 years, 2023 until 2025, even though in this year, 2025 and 2024 and 2025 is La Nina fase, but in this data, we can see that the forest and land fires and drought is still high. So it's maybe because the local climate condition and also vulnerability environmental condition in Indonesia area. So why satellite-based rainfall is important? We all know that the ground-based data is very accurate, but in Indonesia is very limited, and also radar data is have limited coverage, and we need to fill the gaps between this data. So satellite data is can fill the gaps between ocean and land. There are no rainfall data. So satellite base is based on area grid average and also nation coverage and full land ocean coverage. So this is overview of GSMaP satellite precipitation already explained by Dr. Moka. So GSMaP satellite precipitation is based on GPM core observatory. There are DPR and GMI, GPM microwave imager. So this data is only global. Rainfall data, spatial resolution is 0.1 degrees, approximately 10 kilometers, and various version, real-time, long-term gauge adjusted. And disadvantage of this data is can capture the rainfall even in the lack of ground observation. And this data is globally, continuously, and have same spatial and temporal resolution. And this data is open and freely accessible and also long-term archive since 1998. And this is GSMaP products. In GSMaP products have based on multi-satellite and also base gauge adjusted, usually using NOAA or CPC daily precipitation. In based on multi-satellite, there are GSMaP MVK, which is the standard data with 3-day latency, and then GSMaP NRT or near real time with 4-hour latency, and GSMaP now real time with a few minutes latency. And in the below is gauge adjusted using NOAA or CPC daily precipitation. Is also GSMaP gauge, the standard product with 3-day latency, GSMaP gauge NRT with 4-hour latency, and GSMaP gauge now a few latency. So we all know that the standard product is have higher accuracy but lower latency, and also in the real time and near real time is have lower accuracy but better in latency. So the next is GSMaP versus surface observation and versus radar. In this screen, we can see that GSMaP can capture the rainfall in several area in Indonesia, but we can see that in surface observation they are very limited at just capture in one specific point, but in the radar also have limited coverage range, but in GSMaP, we can see the full spatial rainfall data with continuously and also with same spatial resolution. We said that we also using GSMaP already explained by Mr. Nanda. We have NWP output. There are EFS, KAWO, NWP, WRF, and access. We can see that in this model, we can use GSMaP for eyeball verification and also grid-to-grid verification with using the GSMaP rainfall data. We can see that for rainfall pattern, I think is quite good in all the model of our model. We can see that in the ocean area, we can clearly see the same patterns, but in the land area, especially in Rio and Rio Islands, we cannot see in this model, but in the GSMaP, we can see that in Rio and Rio Island have a heavy rainfall, maybe extreme rainfall too. So we move to consecutive dry days. The consecutive dry days or CDD is defined as the maximum number of consecutive days with daily rainfall below a specific threshold, which is we are using rainfall below 0.5 millimeter per day, because this rainfall can be accommodate the drizzle events. CCD is one of the precipitation extreme index recommended by the expert team of climate change detection and index. Increasing CDD value are associated with higher drought and wildfire risk. So CDD is the maximum number of day without rainfall, and the threshold is below 0.5 millimeter per day. This is how we calculate it. In post 1, we can see that the day without rainfall is just 1 day ago. So the CDD is 1. And in the post 2, we can see that number a day without rainfall is 23. So we can see the classification is long. And in the post 3, we can see that the day with rainfall is still occurs. So the CDD is 0, no drought and rainy. In the post 4, we can see that the day with rainfall is 12 days ago. So we can classification as a moderate. In the post 5, we can see that the day with rainfall is 9 days before. So we can classify as a short. And in the post 6, no rain since 48 days, which is very long classification. And in the post 7, no rain since 65 days ago. So we can classify as extreme drought. This is the example of consecutive dry days monitoring by GSMaP data in the left screen, and based on surface observation in the right screen. We can see that this data have a similar spatial pattern, which is in western part of Indonesia is dry condition, and also in the Riau and Jambi also have a dry condition. And we next move to the data processing workflow. Firstly, we download data from JAXA server, and then we use the data with extraction, and we use the threshold daily rainfall 0.5 millimeter, and we using automatic scripting using Python. And the next is we disseminate into BMKG platforms and websites, including we are also storing and archiving in our database. This is case study when El Nino moderate case occurs in Indonesia. We can see that in CDD data impacted nearly 80% of the archipelago, with the most severe CDD observed in southern Sumatra and Java, and also Bali and Nusa Tenggara, and South Kalimantan and Sulawesi. This CDD data also in the data of BNPB, we also occurred drought and wildfire, recorded a total 174 drought case, and also 251 wildfire. The next is the limitation. GSMaP limitation is we are know that GSMaP is indirect satellite rainfall estimation, and already explained by Mr. Nanda that in some area GSMaP have underestimates and usually underestimate, and also in have higher errors in mountains area. And CDD also have limitation that CDD only measure dry days and also ignore soil moisture and evapotranspiration, and very sensitive to the threshold that we are using. So in the error propagation pathway, we can see that a satellite have a bias. So this bias can be inaccurate rainfall data, and the accurate rainfall data can make a wrong threshold classification, and the make broken dry day sequence and misleading drought monitoring. So the key is GSMaP errors can propagate into inaccurate CDD result, but we also complement with in this index like SPI or SPI for reliability. And the last is the conclusion that we are discussion that GSMaP coverage is very consistent and also have high resolution rainfall data. Especially we can see rainfall data in the remote and ocean area. On CDD monitoring also in this equation is very simple and very fast drought indicator. This is very good for early warning or drought and fire risk. And beside that, GSMaP and CDD also have limitation such as satellite uncertainty and also CDD sensitivity. So we must analysis using this data is integrate satellite data, also ground observation and radar data. And also we can complementary index like SPI or SPI to monitoring drought condition and wildfire risk in Indonesia. That's all for me. I will return back to moderator. Thank you.
Thank you, Mr. Ashraf, for the nice presentations. All right, now we will move to the question and answer session. For all participants, if you want to ask question, please raise your hands or you can type in the chat box. I think we question from Mr. Nanda to Dr. Maika. So thank you for impressive presentation. Dr. Maika, you can see the question in the chat box. Thank you for impressive presentation. I've just checked the nowcasting product of GSMaP, and the latest initial forecast is 20 February 2029 and 2026. Is there any real-time product for nowcasting? Thus we can use it for our operational. Dr. Moka, you can answer.
Thank you very much for the question. So actually, we're now working on this research hard to make the nowcast product can be used for the operational purposes, but relatively the accuracy for the nowcasting or prediction data set is still challenging comparing to the GSMaP past durations, statistical information, and the near real-time version and the real-time version. So we are now working to make it more validated product. But yeah, thank you very much for yeah, we understand that the nowcasting product is there are many user needs for this field. So yeah, I will yeah, let you know once the product is ready for the operational purposes.
Thank you, Dr. Maka, for the answer. So next is, yeah, Bodo, please, Bodo.
I think Nanda has his hand up as well. Maybe Nanda would like to follow up what Mukesan mentioned. So I'm happy to step back for the moment.
Yeah, thank you, Bodo.
Okay.
Yeah, I have a following up question. So our challenge in Indonesia for nowcasting is detecting the rainfall initiation or cloud initiation. So in this GSMaP nowcasting, is it possible to capture that rainfall initiation?
Thank you, Nanda-san. Yeah, very good and yeah, difficult question. And yeah, actually the accuracy of the nowcasting, there are two methods basically to generate the prediction, future information. And one is the nowcasting method using the propagating to the future direction, like a few hours after the current status. And the other one is using a numerical prediction model, and we calculate more physically based yeah, information. Maybe Nanda-san already understood. And yeah, the nowcasting, we can technically we can do it by using the cloud motion vectors and the Kalman filter approach that we already used for the GSMaP now real-time version. So technically, yeah, we can do it, and we can provide the information to the users already as a GSMaP Riken nowcast product. And in this prediction field, we are collaborating with Riken, which is a research institute in Japan, and they have many experiences about the predictions or data simulations strategies. So we are now collaborating to use not only the propagating using the cloud motion vector, but using artificial intelligence, very new techniques to generate some more effective, yeah, better nowcasting product, but still under the development. So I'd like to proceed with research activities, and yeah, we'll let you know once the product is ready. Thank you very much.
Thank you very much, and hopefully it can be released soon.
Yes, thank you very much.
Thank you very much, Nanda and Dr. Moika. So please, Bodo, if you have any questions.
Yeah,
Okay.
maybe. So first of all, thank you very much, Imaji-san, for the presentation. I think during our Australian VLab Centre of Excellence regional focus group meeting some time ago, we had actually Yoshida-san present also about it. Now, what's interesting about this was that GSMaP, it really, that presentation, I think this one as well, really stimulates sort of discussion about the use of GSMaP, and it was great to hear from Nanda how the limitations over the Indonesian area. But one of the things I just wanted to, just as another idea about how GSMaP could be used in us, and since Yamaji-san, you mentioned about AI, it's a perfect segue. So I'm just wondering, is it possible I could very briefly share my screen? Because I just want to show some highlights, just a couple of slides. Is that okay?
Yes, madam.
All right, so I'll just see how that works, but I'm sharing my screen at the moment. Can you all see that?
Yeah, we can see.
Great. So this was from the Australian VLab Centre of Excellence Regional Focus Group meeting of September last year. And again, it carries on from Yoshida-san's presentation and some of the ideas out of that. And one thing you'll notice is on the top of the slide, these are all forecasts generated by AI, artificial intelligence. It's the AIFS ECMWF. And they have, as you can see, total column water, rain and mean sea level pressure, and total cloud cover. But the bottom one in particular is how we try to verify the forecast. And as you can see, it's over the Indonesian region. Doesn't quite, I think it goes down toward maybe Okinawa, not quite all of Japan, but anyway, Australia as well. Now, we focused upon looking at the 12-hour predictions of this AIFS ECMWF, and this goes out to 15 days, this forecast. It's AI-driven. Comparing it against JAXA's 12-hour precipitation, the time periods match up perfectly. And as you can see, if I were to just show a couple of slides, we're then able to compare the single AI-driven model with the ensemble, which looks a lot messier. It doesn't look quite, how can I say, there's lots of inaccuracies there. So it's very interesting to be able to evaluate this. This, by the way, is 204 hours out. And then you compare it against the non-AI, and it's totally, so it's actually a means by which you can use the JAXA GSMaP in order to, in a sense, give a first order verification of these AI-driven models that applied over a large, synoptic broad scale, going out to 15 days potentially. So I just want to bring that to the attention. Now, one thing I did note too, and it was pointed out to me by one of the attendees, and if we look at this, this is actually the 204-hour forecasts, but over Indonesia, and maybe that's where, as was mentioned by Nanda, where maybe there are some limitations in the JAXA product over the, say, over mountainous regions. But nonetheless, over the oceanic region, over the broader domain, this is, I think, a really good way of applying a GSMaP for a 12-hour forecast, with a 12-hour rainfall accumulation, comparing that with forecasts that go out to 15 days, 14 days, 13 days, 12 days, and so forth. And so, again, just highlighting the fact that this is, of course, what Nanda mentioned, the limitations over land, keeping that in mind. But here's another example where we have two different models, one which is the AI-driven one on the left-hand side for a tropical cyclone off Australia. In the center, there is our access model, and on the right-hand side is the JAXA data as well. So I just wanted to bring that to your attention. And to finish my contribution is I have advertised a GSMaP during our advanced tropical meteorology subject. So basically, we get our international students. Last year we had from PNG, Solomon Islands, and also from Singapore, to listen to the recordings, similar to the recordings that you're making at the moment of Yoshida-san's presentation. And so that they then have to comment on that, and it brings it's a way of disseminating this valuable information. That's all I want to mention. Just the idea of applying GSMaP maybe to testing these new AI-driven models, and of course, disseminating the presentations such as the one which Yoshida-san did some time ago, and now that Yamaji-san's doing. Thank you.
Thank you for the sharing information. Okay, for other presentations, if you have any questions, you can raise your hands and type in the chat box. I think we have one question from Batru from Guinea. Thank you so much for these brilliant presentations. Are there any conditions for using this satellite? I think this question for Dr. Moika. Dr. Moika?
Yes, thank you very much for your question. Yeah, actually, before the registration, we provide the data policy information at the registration web page. So you can check the data policy before the registration. But basically, the data set is freely available for the users. Is it okay?
Okay. Thank you, Dr. Moka, for the answer. So, any other questions? Okay, I think it's enough. Okay, so finally, we have reached the end of this presentations today. So I'd like to say thank you to all presenters for the great presentations and to the participants for their active participations. Okay, thank you for your attentions. Thank you, Dr. Moika. Thank you, Mr. Nanda, and also thank you, Mr. Aska, for the presentations today. So see you in the Indonesian Philip RFG meeting on the April 2026. Good morning, everyone, and bye-bye.
Okay, bye. Thank you.
Thank you, everyone.